Hi everyone, I'm Takashi Menjo from Entity Software Innovation Center. Today's theme is how can persistent memory make database faster and how could we go ahead? Okay, let's start with persistent memory and PostgreSQL. Persistent memory is a new type of memory technology. It's byte addressable, non-volatile, and faster to access than disk. It's already available on major operating systems such as Windows or Linux. And persistent memory programming is encouraged by PMDK, a dedicated set of libraries and tools. So we can get started to use Pmem. But the question is, for what application we should use Pmem? I think it's database. And for us, it's PostgreSQL. PostgreSQL is one of the relational database management systems. It represents data as two-dimensional tables. PostgreSQL is disk-based database. It stores tables, indices, and other data on disk. PostgreSQL has been developed as open source software by many contributors all over the world. Entity has also contributed for over 10 years. Since 2017, we have tried to apply persistent memory to PostgreSQL to make it faster. Here is how we have tried to make it PMEM-aware. We have taken 3 steps, that is, using Pmem as an alternative of disk, replacing File.io API with PMDK, and redesigning architecture. Today's main topic is how we have tried redesigned PostgreSQL architecture. It was challenging, but more effective for performance improvement. In this presentation, I will show you how the PostgreSQL architecture is and how we have redesigned it. Then, its evaluation. I will show performance and profile results. Finally, I will talk about how we could go ahead to make the database much faster with persistent memory. So first, let me talk about PostgreSQL architecture and its redesign. This is overall architecture. Transaction data comes from top to bottom. In the middle, there are server processes called Postgres, and their shared memory and called the shared buffer. Note that Postgres supports multiprocessing. In this figure, there is only one Postgres process, but actually there are multiple processes. It takes 6 steps to store transaction data to disk. First, a server process receives a transaction from a client. Then it updates tables, indices, and related stuff on the shared buffer to process the transaction. And third step, the server process stores transaction log records. We call that log WAR, write ahead log. WAR contains the delta of the updated tables, indices, and so on. It's used for recovery when database is crashed. WAR is buffered on the ring buffer called WAR buffer. And step 4, on transaction commit, the server process writes WAR out of the WAR buffer to WAR files. This is done synchronously. That is, the server process waits until the WAR hits the disk. After that, the WAR gets durable on the disk. Then step 5, the server process sends an acknowledgement to the client to finish the transaction. And that's all for transaction processing. But wait, the updated tables and indices are still on the shared buffer. The server process has to write them back to data files on disk. When? It's checkpoint, the step 6. Note that checkpoint is asynchronous with commit, so the database might crash before the checkpoint completes. In such a case, do we lose the updated data? No, we can recover them by applying the wall to the data files because the wall contains the latest depth of the tables and other stuff. So we have two data flows. One is logging, left side, and another is checkpointing, the right side. Now, our question is, which is more critical for transaction performance? The answer is logging, because it's synchronous with transaction processing. The server process has to wait until the wall hits the disk. If the disk is slow, the process will wait for a long time. We have focused to improve logging by using PMEM. PMEM is fast and non-volatile, so it should be good for logging. Now we look into logging architecture. It consists of two levels. The first level is DRAM and the second is disk. The reason of two level is because it gains much performance when using disk. As we know, disk is worse at small and random access than DRAM. If the server process writes, log records one by one and directly to the disk, the performance should be very bad. Buffering makes disk access large and sequential, and such access is suitable for disk. Starting from here, we have applied PMEM to logging to make PostgreSQL PMEM-aware step by step. The first step was straightforward. We used PMEM as an alternative of disk. We create a PMEM-aware file system on PMEM and use it for WAR files. It bypasses page cache to write WAR on the buffer add to PMEM directory. And we use PostgreSQL as is, that is, with no change. It calls the same API as before, such as InPosix, lseek, write, fdatasync, and so on. In this step, we can use PMEM without any change on PostgreSQL. But please note that PostgreSQL itself is not PMEM-aware yet, and its logging architecture is still two-level. Second step, we changed a few parts of PostgreSQL. We just replaced its IO API call with PMDK. My colleague Yoshimi talked about this topic in SDC 2018. We had PostgreSQL map WAR files onto memory space and use functions provided by libpmem to write WAR, such as memory copy, CPU cache flash, and memory barrier functions. This reduces system calls for WAR, such as write and fdatasync. So it eliminates transition overhead between user and kernel space. In this step, we made PostgreSQL a little PMEM aware, but please note that its logging architecture is still two-level. We hadn't dived into its architecture deeply yet. Then we got to have an idea for architecture redesign. In this figure, we have two copies of the same WAR. One is here, and another is here. And the idea is that it is necessary to copy the same WAR twice when using PMEM. Why not store WAR directly to PMEM to improve performance by reducing the copy to 1? If we still use disk for WAR files, the idea should degrade performance. But If we use PMEM, the idea could be possible because PMEM is quite addressable, non-volatile, and more importantly, better at small and random access than this. So we redesigned the logging architecture to single level. We have no more usual war buffer on the shared buffer. There is no war buffer. Instead, we introduced a new buffer file on PMEM and map it onto memory space as non-volatile war buffer. The server process stores war directly to that buffer. Then, on commit, it flushes CPU cache to let the war persist onto PMEM. It is only one copy for each log record. So that's all our architecture redesign. Okay, let's go to evaluation. We evaluate our redesign on the following 2 points. One is transactional performance, and another is performance profile. And to do this, we use PGBench and Vision. PGBench is a standard benchmark program bundled with PostgreSQL. And Vision is a performance profiler for x86 machines. For transaction performance, we measure transaction throughput and average latency, and both of which are reported by PGBench. For performance profile, we check CPU time of each function, especially logging function, in 2 ways. First, we run PGBench as it gives a certain amount of transactions to PostgreSQL server. We expect our redesigned PostgreSQL take less time than the original one to process all of the transactions. And second, we run PGBench for a certain duration. If our PostgreSQL achieves more performance than the original one, it should spend more time for transaction processing functions other than logging. Now we are going to show 5 setups we evaluate. First of all, we talk about the points in common. For all setups, we run PostgreSQL server and PGBench on the same physical machine, but distinct NUMA nodes to get a stable performance. This is because NUMA locality is important for performance of PMEM-aware applications. We pin the PGBench onto the NUMA node 1 and the server processes onto the NUMA node 0. Then the server stores data onto the local NUMA storage. Here we use 2 separate devices. And one is for logs. It can be PCI SSD or PMEM. We'll show the details in the next slides. And another is PCI SSD for tables, indices, and so on. The reason why we separate is to reduce the impact of checkpointing. If we use the same device for logs and tables, their access should contend with each other, and performance should get unstable, so we separate them. And then we run PGBench. When we run it, we choose several values for degrees of parallelism to see the performance variation. Each of them consists of the total number of connections and the number of threads. We refer to them as C and J. Note that J is up to the number of CPU cores for PGBench, and C should be multiple of J. Okay, here are 4 of the 5 logging setups. All of them are talked in the previous section about architecture redesign. For each setup, we give the title shown below. For original SSD, we run original PostgreSQL and use PCI SSD for WAR. And for original PMEM, we use PMEM for WAV instead of SSD. For mapped WAV file, and we modify PostgreSQL to map WAV files onto memory space and memcopy to WAV, memcopy WAV to there. For non-volatile WAV file, we redesign PostgreSQL architecture to store WAV directly to the non-volatile WAV file. And this is the last setup we call no-WAV. In this setup, we suppress logging as far as possible by using the following two PostgreSQL features. One is unlogged table to store no WAV except commit records. There is no depth of tables, indices, and so on. And the other is asynchronous commit to send acknowledgement to the client before writing WAV. This setup is used as a reference of upper limit performance. It's not durable, of course, but probably the fastest of the 5 setups because it spends almost no time for transaction logging. We will check the CPU time of logging functions. So I explain what they are. There are 2 functions for logging. One is XLogInsert and another is XLogFlush. XLogInsert stores WAV to the buffer and XLogFlush makes them durable onto persistent device when committing. Each function covers the range as shown here. And please note that what XLogFlush does is changed, but it is always responsible for durability of the WAV stored in the buffer. And this is hardware, software, and PostgreSQL configuration for our evaluation. And in short, we use 2 18-core CPUs. One is for PGBench and another is for PostgreSQL server. And PMEM is a patch bus, Optane Pmem, and up direct mode. And 6-channel interleaving is also enabled. For other items, please read the handout. Now we show the performance and profile results. First, the performance results. Let me explain how to see this graph. And the horizontal axis shows throughput, and the vertical axis shows average latency, and both reported by PGBench running 30 minutes. For throughput, larger is better, and for latency, smaller is better. So for the entire graph, more right bottom is better. And there are 5 lines in the graph. Each line shows one setup as noted here. One line has 4 points, here, 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 and here. And each point shows parallelism C and J as labeled here. And please recall that each of the sub and the PGBench uses an 18-core CPU. So J, the number of threads is up to 18. Oh, sorry. And throughput gets larger as parallelism gets larger up to 1818. While average latency remains almost unchanged. From there, 1818, only C should be increased. But as C gets larger, throughput comes to a ceiling. While average latency gets worse. This is because the number of connections gets larger than the number of CPU cores used by the server. So such a curve shows a regular relationship between throughput and latency. The introduction is over. Let's see the results. Our redesigned non-volatile buffer, shown as a green line, is more right bottom than the other durable setups, such as original PMEM and mapped WAV files. So it achieves better throughput and latency. Also, it's close to no or even better than when C and J is 1818. It's our future work to clarify the reason. Next, we show the profile results when we get the same amount of transactions for each setup. We chose 36 and 18 as C and J. And first, we focus on the logging functions. And this is a stacked bar chart. Each bar shows one setup. The vertical axis shows the total CPU time of 18 cores used by the server process. So lower is better. And in this graph, from left to right, XLogFlush, a blue part, and each time decreases. Note that no word spends no time for XLogFlush due to asynchronous commit. Among the other durable force setups, non-volatile buffer spends the least time for XLogFlush. Also, the total time of logging decreases. So we can say that our non-volatile buffer reduces logging time. But please note that XLog insert time or for non-commit record, a yellow part, increases compared to the other three. This is probably because Optane Pmem is a little slower than DRAM. XLog insert mem copies word into the buffer. If the underlying memory of the buffer is slower, it takes more time to mem copy. Next, we look into the XLogFlush profile. We divide it into some sub-functions. A non-volatile buffer eliminates the three sub-functions in the middle of the hover, orange, yellow, and green part. They are write and lock functions. The yellow function, XLogWrite, writes word out of the buffer to the files. Non-volatile buffer needs no such writes, so it spends no time for XLogWrite. Instead, it needs CPU cache flush to make word durable. Such flush is included in others, gray part, but its time increases little. And then orange and green functions are lock and unlock functions coming with write. They are used for word integrity. Recall that PostgreSQL supports multi-processing. If two or more server processes write word to the same file at the same time, the file can get corrupted. The lock is used so that up to one server process writes word at the same time. But non-volatile buffer needs no such lock because it doesn't need any write-out. And to sum up, non-volatile buffer eliminates write and lock time. Then we show the total profile. And the red part is for the logging functions. It decreases from left to right. And the blue part, read command, is the function for reading transactions sent by client via network. Its time is almost equal for each setup because the amount of transaction is same and network is also same. Finally, we show the profile results when we run PGBench for 30 minutes in real time. In this graph, the maximum value of the CPU time axis is calculated, not as noted here. It means how much CPU time it would take if all of the 18 cores run full time for 30 minutes. We also show the throughput results as line chart. we can find that from left to right, the logging time decreases and more time is spent for read command and other functions. That is, functions for transaction processing, such as query pass, plan, execute, and so on. We can also find that throughput increases as the read command time increases. This means that we can read more transactions than before because of PMEM and architecture redesign. To summarize the results and evaluation, PostgreSQL can use PMEM better than before by our single-level logging architecture. It improves both throughput and latency. It eliminates log time in addition to write time. It spends more time for reading and processing transactions. So we can say that faster memory makes database faster. And more importantly, PMEM-aware software architecture makes database much faster. Software is important. I talked about how we have got here. From here, I'm going to talk about how we could go ahead. I will also tell you some of my failure stories. First, I found that if we want to get better performance, we should do less flash. When I first implemented non-volatile web buffer, I made it work on XLog insert. I made it flash work on XLog insert. That is, flash just after each record was inserted into the buffer. But it was turned out to be a bad idea. It was simpler to implement than flashing a commit on XLogFlush, but it required more flash operation for each transaction because one transaction may insert multiple log records, while it would commit at most once. It got bad performance, even worse than original Pmem setup, when using Optane Pmem, because Optane Pmem is a little slower than DRAM. So I made it flash on commit. Then it got better performance. Please remember that less flash is important for better performance. I also found that less overhead is important for better performance. As another form of non-volatile web buffer, I tried to map the existing WAV files as web buffer, but it turned out to be a bad idea. It was simple to implement, but it was required to switch to the next WAV file for every time the current WAV file got filled up. The default size of the WAV file was 16 megabytes, so the switch occurred for every 16 megabytes. It got worse performance than non-volatile web buffer due to overhead, such as mapping old file and mapping new one, or page fault for the newly mapped file. In regard to non-volatile web buffer, we make a buffer file large enough and map it just once when the server process starts. We don't need to unmap the buffer until the server shuts down. This leads to less overhead and, as a result, better performance. By the way, I have been talking about transaction logging, but we have other data such as tables, indices, and so on. So how about applying PMEM to such data or redesigning their architecture? For example, could we map data files to speed up checkpointing, or could we store data directly to non-volatile tables or indices? Actually, I once tried mapped data files for checkpointing, but I found that I had to resolve impedance mismatch between file API and memory mapped file. The data files are regular files, so they are extensible. If we write something to the tail of the file, it will extend automatically. On the other hand, memory mapped file requires fixed file size, so it cannot extend while it remains mapped. This is what I say impedance mismatch. There can be some ways to resolve it, but there is no silver bullet. For example, if we pre-allocate their data files large enough, we will not need to remap them, but we would waste the PMEM space. It's critical when we use small PMEM, especially NVDM. Or we could remap the file whenever we want to extend it. This will save the PMEM space, but would degrade performance due to the overhead of remapping. It's a sticky program, and moreover, I'm not sure whether it is helpful for transaction performance or other meaningful performance, because checkpoint is asynchronous with commit. Then, how about non-volatile tables and indices? How about storing and loading data directly from and to the mapped tables and indices? In this way, there is another problem, the impedance mismatch, and that is PMEM speed and capacity. NVDM is as fast as DRAM, but too small to store large tables and indices, so it was not suitable for practical use. Optane Pmem is large enough, but a little slower than DRAM in both load and store, so it may degrade performance, even degrade read-only transaction performance. I think it's a primary issue to be solved, or we should find better ways to use Optane Pmem for such data. Finally, I will talk about PMEM-aware data structure. In this presentation, I've talked about PostgreSQL architecture and its redesign. In addition to that, data structure is also important. PostgreSQL is disk-based database, so its data structure has been optimized for disk, and we kept it for compatibility. But if we changed it to memory-based structure, the program will be more flexible and optimized for PMEM. For the first example, PostgreSQL has separated its internal data into pages with a default size of 8 kilobytes. But PMEM supports finer-grained access size, such as byte or cache line. So we can read or write the data what we want without waste. Second, PostgreSQL has arranged its data, especially logging data, in a sequential manner, because this is not good at random access. But PMEM is better at random access than disk, so we wouldn't need serialized data, and we could make its structure more flexible. Third, PostgreSQL has used byte offset for data reference, but PMEM is memory, so we can use pointers for reference. The libpmem object library in PMDK supports such persistent memory pointers. All of them are our future work. Okay, let's wrap up. We have proposed our non-volatile wall buffer to the PostgreSQL developer community. If you are interested in or you want to try our proposal, please access to this link or search the web as written here. The latest patch set is version 3 or might be version 4 if I submit a new patch set before this video is broadcasted. Feedbacks are welcome. We also submitted a mapped world buffer patch set. We made it based on the Yoshimi's presentation in SDC 2018. Please access these links for details. That's all for my presentation. Thank you very much.